Welcome to week 10. In this week, we're going to discuss about operations for LLMs. So think of it as MLOps for LLMs. Again, the topic of LLMs is extremely popular right now, given the hype around generative AI. So we're going to discuss a bit about what LLMs really are and which aspects of the operations around LLMs that you would have to watch out for. We're going to discuss best practices, and in this specific week's lectures, we're going to talk specifically about the nature of, how the LLM building process itself is going to be, something that you'll have to carefully engineer, apply principles around CI/CD on top of it, versioning, etc. And in the next week's lectures, the week 11 lectures, we'll talk more about um, topics related to governance, security, performance, cost, trade-offs, etc. On LLMs. So let's begin. We need to first, have the common understanding of, which aspects of LLMs are we going to spend a bit of time on. Unlike the uh, popular press, which has really hyped up the capabilities of LLMs, we're not going to discuss that in this week or in the next week, because that's already well established. It's evident, and you'll have other courses where you can dive deeper into LLM architectures, building your own LLM, etc. Whereas I'm going to spend more time on what happens around the LLM. So let's take a look at and understand what these activities are. So at the heart of it, the LLM is defined as a fairly advanced AI model, which is trained based on language datasets, right? Which is basically text data. The model is trained to understand and also generate language token by token. And the nature of the architecture, which is a transformer based architecture, has such power and potential that the same mechanism of token based training can actually be used for a wide variety of tasks. It could be uh, text comprehension, it could be image analysis, it could be the ability to generate summaries, etc., etc. So uh, the LLM definition itself is fundamentally one about predicting the next token of text, right? That's how it works. That's how it fundamentally is engineered. So in order to do that effectively, it needs to understand what is the current context in which it's needing to extrapolate and predict the next token. So that context is captured into what's called as a context window. So I've shown that here. So let's look at LLM as a black box which has a context window. To this LLM, the customer or the user, like you or I, if you have used ChatGPT, then we have done this left, right, and center. We provide different types of inputs. The inputs have different formats. It could be text data, it could be binary data, it could be image, it could be audio, video, visual, whatnot. So that's called more broadly multimodal input. So these data sets together are provided as part and parcel of English language sentences and paragraphs and constructs, which are called as prompts, and then the LLM gets back with responses. In aiding its response construction, it uses a variety of tools. One of the most common tools it uses is being able to browse the web. And when it browses the web, it's able to search as much as what we are able to do, right? Almost similar to human capability. It's also able to execute programs, which means it's able to generate programs in the first place. Again, if you look at it as a token prediction engine, um, it's predicting tokens to fill in for the program syntax such that the program is designed to do something specific and produce an output, and that output is then used in the context of whatever the LLM is trying to do. So for instance, if you have asked anytime ChatGPT to summarize a simple table of data and give you the number of counts of occurrences of a specific word, right? It's generating Python code to do it. It will give you the Python code also after it's generated, and the Python code is generated token by token, right? And it looks as though it's writing the code, but it's actually generating by predicting the next token. And then why would it write that particular type of Python program? Because it's been It's looking at the entire Python program as one prediction for what is required in order to answer that particular question. So it's a series of token predictions. That's how you should look at it. And the third tool that LLMs typically have access to is a database or a data store where documents, data sets, etc. are stored. So if you look at other LLMs also potentially, like specific LLMs, which have extremely good capability for specific tasks like image recognition, audio recognition, translations, etc. Those are also various LLMs having APIs which are available for this main LLM to use as the tool. So broadly, variety of different types of tools exist or are at its disposal for the LLM to construct responses back. And each of these different types of LLMs that you build, in this case, this one parent LLM that you're looking to build, comes from a multi-stage build process, right? In stage one, you go through this entire data crunching of the World Wide Web data, which is massive data sets, one of the world's largest data sets. So this stage one is called as pre-training. And in stage two, you take that pre-trained model, also called the foundation model, and fine-tune it to specific tasks that you want to do, right? The specific task could be a domain-specific task. Like for instance, you want to build an LLM for working with your insurance domain, right? So that you can respond back to customer service requests where customers want to renew their policy or they want to ask whether certain medical coverage exists for a condition they have like diabetes, etc. So the fine-tuned model is the one that's answering those questions in a way that's precise and correct. The foundation model by itself might have other problems associated with lack of specificity, right? Hallucinations, etc., etc. So we'll talk a bit about it later on. So these are two stages of how the LLMs get built. The stage one, which is pre-training, like I said, happens on massive data sets, and that massive data set is not something that you crunch through on a daily basis. In fact, not even weekly, not even monthly. In most cases, the large companies that work on foundation models like OpenAI, Meta, um, Anthropic, AWS, Microsoft, etc., they all try to do this on a yearly basis. And then the foundation models in turn, like I said, can be used for fine-tuning, a variety of different use cases. The fine-tuned models are what gets produced on a weekly basis. I mean, weekly is order of magnitude. It's definitely not yearly, can be weekly, fortnightly, monthly. And then finally, there is stage three, which is the actual usage of the LLM. So in that sense, the LLM is used as an API to which you provide prompts and then you get responses. The responses can be constructed to be programmatic. Like for instance, you can ask the LLM to give you back a response as a JSON so that you can take that output and integrate it with your program. So that's all different types of usage. So three stages: pre-training, fine-tuning, usage. With that as the context, right? No pun intended. So let's take a look at how LLMs change the dynamic when it comes to operations. And this is going to be in contrast with classical ML and deep learning as well. So I'm going to just plot these as three different columns: classical ML models, deep learning models, and LLMs. If you look at training time, classical ML is really fast, right? Deep learning takes a bit longer. LLMs obviously is the longest, especially the pre-training module is super long, right? It takes weeks on GPU clusters. The model size itself is a significant variable. Classical ML is small, deep learning tends to be large, whereas LLMs are extremely large. In fact, the jargon, or rather I should say the packaging that most LLM tools providers use, they segregate between proprietary LLMs, proprietary foundation models, and open foundation models. And even within open foundation models, they segregate between open weights models and open source models. And the reason for that is one of the big reasons is model size, right? And obviously intellectual property, etc. All of those are other reasons, but model size plays a significant role on how ready an LLM is for consuming. what data does it need for a model to be built? For classical ML, it's small to medium data set. Big data is also possible. Deep learning is large data sets most often. LLMs are extremely large data sets called web scale data sets, right? The compute requirement for classical ML is minimal. Deep learning requires a bit of GPU to make it faster, but you could run some deep learning algorithms on CPUs as well. But for LLMs, it has to be GPUs, right? Otherwise, you're stuck with extremely long runtimes. Task flexibility, meaning what kind of tasks are the output models efficient at? So if you build a classical ML to solve a specific problem like iris classification, you can't really use it for audio detection. It just doesn't work. Deep learning has a bit of generalization possibility. Something that's good at recognizing handwritten digits can also recognize handwritten letters. So that generalization is a pretty useful feature. Whereas for LLMs, the um, the reason why it's popular and it's hyped up so much is because of this general purpose nature. It's got very wide applicability on a lot of different types of problem statements. Explainability is inverse. Classical ML is a lot more explainable. We can use SHAP. We saw it in the last week's lecture, and try to explain why a specific output is happening for a specific sample. Deep learning has lesser explainability. I'm saying medium only as a spectrum choice, right? But in practice, if you see, deep learning also has very poor explainability. LLMs are absolutely no explainability beyond just token prediction probabilities. So part of the reason why um, explainability manifests in this way is because um, LLMs tend to work with noise data and also perturb even existing data which might be of high quality. That's how it's actually able to generate hallucinations, right? And those are problematic. And that's also aiding in this perception that it's not explainable. Inference speed, once the model is generated and it's deployed, how quickly can it run to generate a prediction? Classical ML can be super fast. Deep learning also can be relatively fast if you do the right levels of compression. So we spoke a bit about it before, but the big deep learning models are not really fast in terms of inference. It still takes a bit of time, even on GPUs. Whereas with LLMs, the relative speed is significantly slow. But our experience with like using ChatGPT, etc., is not that slow. That's because it's got a lot of, I would say, optimizations done in the back end. Relatively speaking, it's slow, but human scale latencies are, different. I would say, like at human scale latencies, models look roughly the same. Security risks, classical ML has some new types of risks. We saw that deep learning introduces even more new types of risks like adversarial images, etc. Whereas with LLMs, the security risks are many more. The surface vector for attack for LLMs is significantly more. So the examples would be, what if prompts get hijacked in the middle and something else get injected there? Or what if destructive prompts are given? How does it behave, etc., etc. And then transferability, meaning that once the model has been learned in a certain way, can I take that learning and apply it in a different context? So it's kind of like task flexibility, but it speaks about it from a perspective of development effort, not usage from an output perspective. So transferability of the code, transferability of the model itself is very poor for classical ML because it's geared towards a certain task, which is geared towards a certain data set. In deep learning, the architectures broadly remain the same. Usually what we end up doing is we just remove the final layer and fine tune it for a slightly different problem statement. So the transferability of that architecture, of that weights themselves are there to an extent, right? That's why I'm just calling it as moderate in this spectrum. Whereas with LLMs, the general purpose learning ability that it's produced also makes it amenable for zero shot or few shot learning on brand new contexts. What does zero shot mean? Zero shot means that um, the LLM that is useful in predicting the next token in a um in a Shakespeare-like story is also useful with um, minimal to no guidance for generating the next token in a Python code, right? Shakespeare story generation, Python code generation, both happening from the same LLM with minimal guidance. In fact, it's zero guidance is zero shot. If you give it few samples and say this is what I want you to do for this input, produce this output, that's called as few shot. With LLMs, you can do that. You can't do that with deep learning or classical ML. Okay, having said that, let's now take a look at what challenges LLMs bring to the table as a result of these key distinctions between classical ML and LLM specifically. Okay, so like we discussed before, there are three stages of interaction with an LLM. One is, of course, where you pre-train an LLM and create a foundation model. The second is you take a foundation model and you fine-tune it to specific tasks. And the third is you take a fine-tuned model and directly use it, or you take a foundation model and directly use it. So pre-training, fine-tuning, usage. There are challenges across all three stages. We will take a look at it from an operations perspective. I'm not talking about the challenges with respect to accuracy, with respect to feature, matching with the output that's expected, etc. Those are different problem statements. That's more pertaining to the functionality of the LLM, why you're building it, etc. Whereas here I'm talking about the operation side. So in the pre-training stage, one of the most significant challenges is the data, right? We're talking about massive amounts of data, like the biggest data sets you can ever imagine. Being able to take those data sets, crunch through it, and then generate a foundation model. I can tell you that in all practicality, most of you will not be doing this, right? Because the access to the type of resources, to the massive data sets themselves, and the talent pool and the business investment climate for doing this on a regular basis only exists with a handful of companies in the world right now. More action is coming in the form of governments, in the form of private players, but at the end of the day, it's still a very significant exercise, daunting exercise with a huge budget overlay. So this is something that is not easy to do. LLMs need terabytes of diverse, high quality text. It's not just random text, because the more random text that you put in, the more garbage you're going to get out. So this is a significant challenge. The second is the computational resource, because if you have large data sets, the ability to crunch through requires the access to latest and greatest of compute. So the requirement for compute is extremely high for the pre-training stage, right? Specialized hardwares are required, and that's something that all these hardware companies are innovating on, day in, day out. You also need the ability to train the model in parallel, because no single computer is ever going to be able to fit all the data. So a lot of big data techniques come into play. Okay, pre-training, that's one. The second stage is fine-tuning. So in my opinion, a lot of you, will get a chance to work on fine-tuning, because that's something that's more accessible. It doesn't require as much compute, it doesn't require as much data, but it still requires care, right? It still requires operational maturity. So let's talk about that. The first is control and interpretability, which means that for fine-tuned models, how do I control for the specific outputs that it needs to produce while not losing the power that it can that it possesses inherently to work on variations of those problem statements, like the transferability to other uh, similar tasks with zero shot or few shot guidance. So that control and that ability to explain what is happening is a challenge, right? You can't take a fine-tuned model and guarantee it's going to work on affiliated or ancillary tasks, or will provide outputs in a way that's explainable, that's interpretable. So that's a challenge you'll have to work through. The second challenge in fine-tuning is continuous updates. that's required because the data is new, right? The foundation models have become outdated. So here's something I want to point out, right? If you look at most releases of foundation models like GPT-3, GPT-2, GPT-4, etc., it almost always comes with a caveat that it's got the view of the world as of a particular date, because the act of collecting that data set and making it available for the pre-training, which happens over weeks on expensive GPU clusters, produces a model which is already not up to date with the most recent activities in the world. There are private efforts from private companies which have tried to bridge that uh, staleness issue. But if you build your own fine-tuned model, you'll have to work through this topic yourself. How, how do how do you stay abreast of new developments in your activity, in your domain? So the LLMs become quickly outdated. So the updating is something that is not easy, right? You can still do it with automation. So CI/CD plays a role. We'll take a look at it in a couple of slides. Then comes the usage stage, and this is where most of you will spend most of your time, if not all your time. In the future, like, we're going to have LLMs be incorporated in almost every sphere of our digital existence. So we're going to have a lot of usage across a lot of different domains and applications. So what challenges exist? First is latency. Relative to DL, relative to classical ML, LLMs have significantly more latency with respect to inference. For human scale inference, or rather human scale latencies, maybe it's not that much, right? It depends on the problem statement. But the moment you start putting LLMs within applications, these latencies add up very quickly. So let's take an example. If you are building a WhatsApp LLM, and that WhatsApp LLM has to converse with an individual in local language, right? So it needs to be able to understand their language, Hindi, Tamil, Marathi, whatever, and it needs to be able to respond back. And the ability to respond back comes down to real-time um, latencies for comprehending speech, translating speech, and generating speech. That's a big challenge, right? The latencies of current day LLMs do not, really work out of the box for local vernacular languages in India. Having said that, most of the big foundation model builders are giving variations which are, tested out for English language, real-time translations, etc. So maybe it's a matter of time, but for now, latency is an issue. Hallucination risk is a huge issue. Everybody knows about it. Anybody who's worked with LLMs knows this is a risk that they face. So this risk is significant, right? You wouldn't face this as much with classical ML or classical DL, because there it's evident as misclassification, and misclassification becomes a metric that you can measure yourself against based on validation data and come back and correct for. Whereas here, the hallucination is about generating wrong answers but doing it in a way that's confident. So the confidence is misplaced, and it's hard to detect that without having appropriate fact checkers or verifiers built into the process. The LLMs themselves are large, right? That's one of the reasons why managed LLMs are the rage, right? Most usage works from managed LLMs. Like, you don't take GPT-4 from OpenAI and deploy it, even if you could. It's very large. For instance, even Claude, when I think the 3.5, if I remember right, when it released it, they didn't release it, the very large version. The very large version was held as a hosted model by Anthropic directly, or through AWS or Microsoft, or even GCP. They released only an open weights version for the less heavy model. The reason being, the model size is very, very large. And if you're not careful, you'll very quickly rack up the costs associated with hosting such very large models. There are techniques available to simplify the models, distillation, quantization, those are all techniques. I'm sure you'll learn more about them in a separate course on LLMs. Security and abuse is something that you'll have to watch out for as a challenge when it comes to using LLMs. So here, different types of security problems exist. We'll talk about a bit about it in next week's lectures: prompt injection, data leakage, etc. So these newer types of security risks are rare in classical ML pipelines. Classical ML itself has, rare security problems. We spoke about it in the couple of weeks ago. This takes it up a notch even more. And then finally, ethical and bias concerns, which are basically governance concerns. With classical ML itself, we kind of stopped last week by saying that bias detection is an advanced topic. For LLMs, this takes it up a notch again, because the kind of biases that exist with LLMs are not something that LLMs are imagining. They are actually learning as patterns of token predictions from the embedded biases in the data set, right? So it stems all the way from the data set that's used in the pre-training. From there it stems. So you've got to really be rooting for bias detection right at the beginning, which is the massive data set collection itself in the first place. So much larger surface area. Okay, so we'll take a pause here. In the next video, we'll talk in detail about the operations for each of these 3 stages. What can you do for mitigating some of these challenges? It's hard to eliminate them completely. We'll look to automate some of them. We'll look to use some of the techniques that we've already learned in the previous weeks for classical ML. Some of those will apply here as well. Anyway, I'll see you at the other side of the break.